Well, welcome back to Visual Theory 2. And Mondays have become a bit of a technical class. The last few weeks we've been looking at lens design, and today we're going to be thinking about how a digital camera creates a full color image. And um, well, let's just look at the lesson plan here and start off with this. So, the question: how does a digital camera with one sensor make a full color image? Today we're going to be thinking about bit depth and also a CFA, which stands for color filter array, or a Bayer filter. Bayer, the name of the guy that designed it, Bryce Bayer. We'll look at that in just a moment. And with all of these technical classes, we need to retain this information. So next week there's going to be a pop quiz. It'll be based on the lens design and what we're going to be covering today. So notebooks out. There, you need to get your brains in gear. It's not straightforward. It's not easy to understand, but hopefully we're going to be able to grasp the basic principles of what we're talking about here today. The objective for today: to introduce the basics of how a digital camera with one sensor creates a full color image and how bit depth impacts tonality. There's no assignment today, but coming on Thursday, we're going to be thinking about our matching eye color assignment. And well, on the lesson plan last week, we were thinking about the second part of lens design, thinking about lens flare and the circle of confusion, thinking about how the F number, the aperture, impacts depth of field and the technical aspects of how that actually works. So notebooks out. The main heading today: how does a digital camera work? And the first subheading with that is: what is bit depth? Your reading assignment, page 161, in your main London Stone and Upton book, Photography. You'll see that there's an inset box in blue. It says bit depth and image quality. I want you to have a read through there. That will kind of reiterate what we're going to be covering in this class today. And on the right hand side, a little bit on resolution there as well. So that will give you some more text information on what we're going to be thinking about today. So, brains in gear. Our image sensor is made up of millions of pixels. The image sensor is located on the focal plane within our digital SLR camera. It takes the place of film. So in a film camera, that's where the film will be, but we have our image sensor there now. There are several different types of image sensor. CMOS, CCD are the two that I want you to learn about and to understand. CMOS stands for complementary metal oxide semiconductor. CCD stands for charged coupled device. Most of your cameras, if not all now, will have CMOS sensors. A CMOS sensor allows for live view. And live view, you can look at the back of your camera, or in a mirrorless camera, you can see a digital image created, and that requires a CMOS sensor to allow you to do that. It paves the way for us to have video technology built into a stills camera, and the cameras that we have now are just phenomenal pieces of equipment, and many video capabilities are within those cameras as well. Okay, each pixel is sensitive to light. So on your image sensor, there are millions of pixels, 16, 20 million pixels are the norm today, and no doubt that is going to increase as well. Although we have seen that there have been camera manufacturers that have taken a step back from just having sensors with more and more image, or more and more pixels on it. That has been the driving force for people understanding the quality of a digital camera, how many pixels it has. And certainly in the early days, it made a big impact. But now it's less of an impact for the output quality that most of us are looking for. Now, if you're talking about high-end advertising and commercial photography, creating images that are going to be seen on a billboard by the side of the road, then yeah, you need to have a higher megapixel camera. And for high-end work, where the demand is for higher quality, that's where medium format and higher pixel counts are really required. But for the most part, for magazine reproduction and for wedding and general commercial photography, we don't need to have the really, really high-end large format cameras. Each pixel is sensitive to light, and we could think of that as being, as light hits a pixel, it generates an electric charge. If it's a bright light, it's going to generate a higher charge. If it's a lower amount of light, it's going to be a smaller charge. Now, our cameras are basically computers, and all computers work on the basis of binary, a 0 or a 1. And you can imagine that being a switch. If we have just one switch, one binary switch, a high electric charge hits our sensor or our pixel, it generates a 1. If it doesn't reach the required amount, it's going to be a 0. And you can have that switch on or off, and that in photography terms can represent a solid white or a solid black, black or white, just two tones. But of course, our digital cameras have more than that. They allow us to see a full range of tonality and a full range of color, which is what we're going to be covering and thinking about today. So the number of intervals that can be measured equals the bit depth. And in computer terms, a bit is a binary digit. It's the smallest piece of information and has a value of a 0 or a 1. Bit depth equals the number of binary switches that can be in our camera or supported by Photoshop. Generally, 8-bit is the start point, and traditionally that's the place that we start, and our camera default is going to be set to 8-bit, although we can increase that setting on our camera to 12 or 16 bits on most cameras. Photoshop, as I say, it supports 8-bit, 16 or 32-bit, and well, as we go on, hopefully we can see the impact that that actually has and the benefit of having a higher bit depth set on our cameras or within Photoshop. So with 1-bit, there is one switch with the options of 1 or 0, which can be represented as black or white. With 2 bits, there are 2 switches with 4 options. If you've got 2 bits, you can have the 1 and 1 lined up, the 1 and 0 lined up, the 0, 1 lined up, or the 0, 0. So it would allow for four tones, if you will, a solid black, a solid white, and 2 shades of gray in between. So if we have a 1-bit sensor, there are 2 options. With a 2-bit sensor, there are 4 options. With a 3-bit sensor, there are 8 options. We can multiply 4 by 2, and we end up with 8. With a 4-bit sensor, we can multiply 8 by 2 and end up with 16 options. With a 5-bit sensor, we can multiply our 16 by 2 and end up with 32. With a 6-bit sensor, it equals 64. With a 7-bit sensor, 128. And with an 8-bit sensor, 256 options. 256 shades of gray, if you will. So this translates into a graduated scale with 256 options, and but it creates just a black and white image. It doesn't create a full color image. For a full color image, we need to combine 3 separate channels, and this is where the magic really begins. And we're going to think about our part 2 in our lesson plan here. What is a CFA, a color filter array? Okay, color filter array. Let's look at some pictures. These are 2 kind of standard ones. The one on the left is the Bayer filter, which is the one we're really going to concentrate on. X-Trans is developed, I believe, by Fujifilm, and but we're going to concentrate on the Bayer filter. Here's Bryce Bayer, no longer with us, but he's the guy that invented this filter array. Due to the sensitivity of the eye to green light, there are twice as many green filters in the array. And if you can draw this, do a grid that's maybe 4 down by 6 or 8 across, and that should be enough to get a sense of what's going on here. Across the top line, green, blue, green, blue. And in your grid, if you just draw a grid, you could put a G, B, G, B, G, B. The next line, red, green. You could do RG, 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 RG. And then the next line again, green, blue, green, blue, green, blue, and so on. And that way you can see that there are twice as many green filters as there are blue and red, respectively. Another diagram here. So we have laid over our image sensor this filter, and it's made up of red, green, or blue filters. And the pixels that go to the red filter, only the light that is red is going to be allowed to shine through, and the green and the blue is going to be blocked out. So things that are green and things that are blue, that light is not going to be shone through the image sensor. Only the red light is going to be coming through. Likewise for the green filter, or the green parts of the CFA, the color filter array, only the green light is going to get through. The blue and the red light is going to be blocked, so nothing's going to come through. Likewise for the blue channel, only that which is blue is going to be seen through. The red and the green is going to be blocked and represent nothing. This is where the magic comes along, where a demosaicing algorithm or mathematical formula guesses what the red value would be in each of these blank spots here to create a full channel, a full red channel. Likewise for the green, the demosaicing algorithm is going to guess what the green value should be in each of the blank spots to create a full green channel. Likewise for the blue, the demosaicing algorithm is going to guess what the value needs to be to create a full blue channel. And we end up with a red, green, and blue channel. The light hits the pixel. In the blue channel, the blue light gets through, but the green and the red is blocked and is not seen through onto that channel. Likewise for each of these three channels here. I'm going to jump to Photoshop and look at a couple of images, and here on the right you can see it's next to the layers palette. We can see the channels, and when I've got all of the eyedroppers switched on, we can see the full color image. But if we look at the image first of all, you can see the orange flower here. There's a lot of red in that. So if I turn off the green and the blue channel, we can see that that flower is very, very bright. It's orange, of course, but the red channel is only allowing the red light through. You can see underneath that the liquid here is very, very dark. And if we just turn on the blue channel, you can see that is now light, and the flower that is orange with a lot of red in it is very, very dark. Let's turn all these channels on. It's a theory that we discussed when we were doing our black and white conversions in digital imaging 1. And I told about the experiment that I did at college using black and white film that was sensitive to red, green, and blue light. It's called panchromatic film. Pan because it encompasses all three colors, red, green, and blue. We took photographs of the same bowl of fruit that had different colors represented in it. The first image was taken with a red filter, and we see it as red because it blocks out the green, and the blue. Not because it's red, but it's because it blocks out those other colors. When we processed our film and then put it into slide projectors in register at the same piece of screen, it's all black and white until we put a color filter in front of the image. And the color filter in front of the red image, only red light, in front of the green and in front of the blue, and when they're combined together, it creates a full color image. And that's exactly the same thing that we're seeing here in digital photography. I'm right at the end of my time, my 15 minutes, which is probably a good thing. So I'm going to cut off right here. Watch the video again and watch the James May video a lot of British humour there.